Hi everyone, good afternoon. Thank you for staying for this late session. I guess it wasn't the food that kept you here. Um, my name is Adam. I'm leading a group of data scientists at PayPal. My group is responsible to answer some of the general questions in PayPal risk. For example, which account belongs to the same person, household, or business. In addition, we are working on general IP intelligence questions such as IP location and IP networks, which I'm going to discuss in this session. I'm going to talk about IP intelligence. So in the fraud and risk domain, IP attributes are a very strong contributor for risk decisioning. I can tell you that IP attributes are the top performing variables in almost all PayPal risk models. Let's look at a very simple example. When someone is logging to PayPal website from a certain IP, we can ask ourselves whether that's the legit user or did someone stole the password and trying to take over the account. If we know that this IP was used successfully before, then obviously that's a very good sign that, that this is a legit activity. And you can think about many more IP-related attributes, such as does the IP location match the user location, or did we see a bad activity coming from this IP? So how we develop IP intelligence? We combine two approaches. The first approach is to directly build variable and correlate them with fraud. For example, looking at how many users use a certain IP in a certain window in time. And we can build thousands of attributes and test them against our fraud tagging, and we can use machine learning and other approaches to make this very strong variable. However, we believe that this approach alone is not enough because it cannot cover hidden and complex relation in our data. On the other hand, IP is actually has a real physical representation in the world. It's lead to some endpoint in the world. If I could hire a private detective and he had the ISP data, he could have tracked this device and say, okay, this IP is located here, its owner is a private person or a corporate, and that's a mobile connection or a modem or perhaps a spoof attempt like proxy, Tor, or something like that. However, when we want to take this approach to enrich our IP intelligence, we are facing a few major challenges. The first challenges is the question I just presented. There is no tagging. There is no source of truth. We do have with data RDNS data that may answer some of these questions, but not completely, and we'll see example for that. In addition, the signal is weak. Even a company in PayPal order of magnitude, we do not, with 200 million active users, we do not see the entire IP range. And for most of the IPs, we have a few or even one login. So overall, if you look on the entire IP space, the signal is weak. And finally, the world keeps changing. Endpoint change, things happen in the world. For example, eBay and PayPal splitted, our IP ranges changed, and this was a real change in the world. So in order to come up with a better intelligence for location and for all the things I mentioned, we are building the basic layer that we call them the IP networks. IP networks is a group of IPs that share the same properties. For example, if your corporate networks has a certain group of IPs, that's a network. In a network, we expect that if user uses IPX, there is a high probability that we'll see him from IPY, assuming that X and Y belong to the same network. And by having these IP networks, we get a better representation of the world, and it helps us to get more, to increase and enhance the signal that we have over our data. So instead of working with just one IP, we can work with a group of IP and aggregate the insight that we see over this IP, and that yields higher accuracy and coverage. So let's look on another example, another consistency example. We have a user, and let's say that the user uses the first IP in this list here consistently and all the time. And suddenly, in a certain day, he comes up with 3 new IPs. So is that bad or good? Assuming you can see this IP, can you see them? So I guess that most of you would say, is this consistent or not? We have some fraud specialists here. So most of these IP are very close to each other. The proximity is very high. And most of the people would say, okay, these IP belong to the same networks. Even that these are not the same IPs, they are consistent. So if you remember the previous example, we would say these IPs should be consistent. And indeed, our first approach in PayPal for IP networks was the IP proximity. Using subnet, for example, the last part of the IP address or the last 2 parts of the IP address, as a sign that these IP belong to the same networks. However, that's not good enough. You may be over-conservative and miss lots of connectivity between networks, and perhaps you over-aggressive, and then you'll connect unrelated networks and enter and fraud can penetrate your networks. So the next logical step is to use WHOIS data, RDNS data, ASDN data that we have on IP. However, this data, as we'll see in the next slide, is also not complete and not always accurate. And obviously, we have the internal data, and we can use our user as agent to learn us how the world behaves, how these IP networks behave. And we are trying to combine these 3 approaches to come up with the best IP networks. Today, I'm going to mainly focus on the last one, how we use internal data to build our IP networks. So I know that that's probably too small for most of you to read. But if you look at this example, the first 2 IPs are significantly different than all the other IPs. The range is completely different. And the ASN data, the WHOIS data, and the RDNS data of the first 2 IPs is completely different than the last IPs. So using proximity and WHOIS, ASN, RDNS data, you wouldn't say that these IPs belong to the same network. However, we saw that actually each user that uses PayPal from one IP is using all the other IPs in this network. So we believe that this is the World Bank networks altogether and not just the last record. So all of these IP belong to the same networks. And that's something we could only extract from our internal data. So how do we use internal data to build IP networks? The first step is to build a graph, a usage graph. So user A using a certain IP and connect and build this graph connecting IPs and users. In this step, one of the most important things is to clean the data from noise. Usually in papers, presentation, everywhere, the first step doesn't get enough attention because it's very tightly coupled with your business logic and data. And what we do in PayPal would probably not be relevant for other organizations. However, I want to emphasize the importance of this step. So investing in this step and extracting all the noise that is built in the system when you're trying to build such graph is very important. And if you don't do that well, all the other steps would fail. Next, the second step is to collapse. We're taking the user activity graph and we transfer it into IP to IP networks with weights between different IP nodes. And finally, we use clustering to find these dense neighborhoods in the graph. So let me explain this slide with example. So we start with a user and we say that user uses an IP. That may seem a very simple relation, but actually even this very simple edge is not that trivial. For example, if a user didn't use this IP in the last year, do we want to create this edge or not? And if your answer is not, then what's the threshold? 3 months, 2 months, 1 month? That's a hard question to answer. In addition, user might have different frequency for using a certain IP. So in our case, this user uses 3 IPs, and 2 of them are shared by another user. So this is the usage graph. And then we want to collapse and build an IP to IP network. So we draw an edge between each IP that is connected by a user. And we want to create a weighted graph for IP to IP. Here we also have multiple questions. For example, this IP here is connected to this IP only by one customer. Do we really want to have this edge or not? That might be just noise. Another question is, we have 2 edges here. How do we create this weight? And keep in mind that this usage can be very frequent or very not frequent, or very recent or perhaps not recent at all. So how do we weight all these activities when we create the IP to IP graph? And finally, after we created this big graph of IP to IP relation, we use community detection to find dense population in the graph. And these dense populations are actually the IP networks. So each color here represents a different network in the graph. And what you can observe is that almost each network is connected to at least one or usually more than one other networks. And that's very obvious, because think about that user doesn't use the same network all the time. They use PayPal from coffee shop, from their home, from their work. So you would always have connection between IPs that are not related, and our goal is to find dense population inside this high background noise. So a few words about this cool part. This is really usually gets all the attention, the clustering, the data, cool data science stuff. So there are lots of clustering and community detection algorithms. The literature is full of them. I wrote a few examples in this slide. And there are lots of papers that compare these different clustering algorithms under different assumptions. My advice is usually this paper, they are very good papers, but the clustering performance is very tightly coupled with your data and the business logic you're trying to achieve. Therefore, it's possible that some algorithm will be very popular, but in your specific problem, it wouldn't perform as well. So my suggestion is to select a few of the top performing algorithms and test them all. Finally, a very important factor for us is the ability to scale, the ability to calculate a clustering algorithm in a distributed way. We are talking about a huge graph. You can think about tens of millions and even hundreds of millions of IP in our system. And we have this graph processing problem, a very difficult one, from running these algorithms. And we are using an Hadoop cluster with thousands of nodes running graphics over Spark. And it took us quite an effort to be able to run these algorithms. I do want to note that our graph is very sparse. Most of the IPs don't have many connections. However, it's highly connected. So each IP at the end of the day leads to another IP. If you heard about the handshake, that you are connected to almost each other person in the world by 4 or 5 handshakes, that's the same thing. So you cannot localize or build subgraphs. You usually need to work with the entire graph at the same time, and here the graphics parallel paradigm is very helpful. The last piece in building IP networks and generally in graph processing problem is how to measure. We want to say, okay, did we succeed or failed? How our performance looks? And more than that, you want to tune. You want to select your clustering algorithm. You want to tune the threshold. You want to be able to answer all the questions we ask ourselves along the way and measure how that affects your performance. So we have a few approaches to measuring the performance. The first and most obvious approach is, okay, let's use external data and IP proximity, the WIZ RDNS data. However, I started this session by saying we want to be better than that, and we want to use all of them. So that's just not possible. The second thing is statistical measurements. I mentioned that lots of papers compare a clustering algorithm using, usually they would look on statistical measurement such as mutual information. Statistical measurements are very important, and we use them quite often to tune our algorithms, but it's just not enough. You can have a perfect, or you can maximize the mutual information, but your performance, the logic that you're trying to find, is not performing as well. In addition, when you select an algorithm, sometimes your algorithms aim toward specific type of cluster, which will reduce, for example, the mutual information, so you will be overfitting your clustering algorithm. Another approach is manual review. Let's put a top of the line fraud analyst. He would look at these IP networks and tell us, did we succeed or not? Obviously, that's not scalable. We can do it on such scale. However, we do want to learn how a human would try to answer this question and use that as a measurement. So let's look at this IP network, very highly connected IP network with many nodes. Let's take an analyst and ask him, do you think that this is a network, and what this network is? And what an analyst would say, okay, he would start looking at this IP and the users and everything, and shortly, hopefully, he would come up with the insight, look, many of these networks are using the same shipping address. So in fact, most of them are, and all these addresses are PayPal offices in different parts of the world. The last one is here in Israel. Our neighbor Google actually doesn't recognize us. Anyway, if you see that lots of shipping addresses are consistent inside these networks, and all of them point to the same logical entity, that really enhance our belief that this is the same IP networks. So how we combine everything up, our wish to use more data, external data, and the fact that we want to measure ourselves. So I'm going back to the usage graph. After we calculated IP networks and everything, we can go back to the graph and enrich it. We can say that two users have the same email domain. That's a good sign that these two IPs are actually in the same networks, because if this PayPal.com, two users from PayPal.com sharing two IPs, makes sense that this is an IP network. We can connect two IPs by RDNS. In this example, we actually want to use this data for a better algorithm later on. So by saying that these IP are connected, we can improve our logic. And as I mentioned earlier, if two users share the same address, that can enhance the probability that they are in the same networks. So by enriching the graph with many assets like address, email domain, and other, we can now ask ourselves, okay, is our IP networks consistent in this asset? Does many of the users share the same address or email domain or any other asset? And we can put a statistical score for that inside each cluster. We can also see whether we have two separate networks, two separate clusters that actually share many assets like address or email domain, and then we would say, okay, perhaps we should have combined these two clusters. And by doing so, we can come up with numeric measurement to the performance of the IP networks algorithm. So summing everything up, IP networks is a powerful tool to build IP intelligence such as location and consistency. We're using graph processing to calculate these IP networks and other IP attributes, and we believe that by combining that in a graph processing, where you can get intelligence for the first, second, third hop in your graph, is very powerful. Thank you. Hijacking the computer, like using a remote desktop, is a very complicated problem that IP itself, as far as I know, cannot solve. We do have a very powerful intelligence I didn't mention here, identifying spoof IPs such as proxies, VPN, Tor, and etc. So that's an excellent question. Some of that will be handled in the data cleaning, because if you have one IP with so many users, there is probably the information over this IP is very low. But even if you have a mobile IP that enters the clustering step, we usually expect that the background noise over this IP or the mobile operator IP would be so high that it wouldn't be clustered. The problem is that we don't have tagging to do this classification. And if we have tagging, then we would have used it to create better networks. So we don't have tagging, therefore we cannot perform classification. And we're trying to find indirect ways to measure our performance and to calculate these networks. Thank you.